Today's presentation is about Flipboard. Is a social aggregation mobile app that aims to transform how people discover, view, and share content by combining the beauty of ease print with the power of social media. This session will give an overview of the data lifecycle. Ashish and Rob will discuss the data strategy and architecture, the power of Python and in-memory processing, and the role of Qubole and Flipboard's Python SDK and other cloud technologies to quickly and easily access data, analyze it, and feed it into other models. And today's first speaker, we have Ashish.
Yes.
Thank you. You take it.
Thank you. Hello, folks. My name is Ashish Thusoo. I'm the CEO and co-founder of a company called Qubole. So today's talk is going to be divided into two parts. The first part of the talk, which I'm going to be presenting, is going to be talking about generally the big data landscape, some of the technologies in open source that have emerged there, and I will also focus a little bit about when you're running, what are some of the issues that organizations would face when running at a very, very large scale, and especially how cloud helps in that. And after that, I'll pass it over to Rob, who will be talking about in depth of all the goodness around Python and in-memory processing and stuff at Flipboard, and that will be a very, very strong use case of how all these technologies are used in real-world environments and in helping there. So to start with, a little bit about myself. My name, as I mentioned, is Ashish Thusoo. I'm the CEO and co-founder of a company called Qubole. Essentially, we offer a cloud-based platform for big data. That's what Qubole does. And before Qubole, I was at Facebook. I was instrumental in building out the data infrastructure at Facebook. I led that team for a number of years. In the process, also created Apache Hive. That was one of my inventions and my co-founder's inventions. So I have been in this environment. When big data was not called big data, it was, from that perspective, I've seen this industry grow and seen what are the advances and changes that have gone in this area. So just a little fact check. So why has big data become so important recently? A lot of this has got to do with changes that have happened in the data landscape itself. If you go back to the 90s, a lot of data that was produced through business applications. This is what I would call transactional data. This is essentially data which would be sitting in a database, created as a result of filling out certain forms or transactions. Banking transactions is a canonical use case on which the whole of the RDBMS industry was built on. So a lot of that was transactional data. But as a lot of things started moving online, as the web expanded and the web applications expanded and the mobile applications expanded, what we saw is a shift in the nature of the data itself. What has become more important now in the last 15, 20 years or last 1.5 decades has been what I call interaction data. This is essentially data which is generated because of entities interacting, whether these could be human beings, this could be machines. And inherently, this interaction data is a lot more unstructured, has a lot more volume, and has a lot more velocity as compared to the previous generation data sets, which are mostly transactional data sets. And that essentially has led to, the previous generation systems are found wanting in being able to handle these data sets and being able to provide tools for processing of these types of data sets. And that's really what has led to the evolution of big data. Now, having seen data infrastructures run and operated for this type of data, of course, the most logical thing that people realize is, you need some sort of an infrastructure that scales with commodity nodes, because this is really, really large data sets. You really have to think about horizontal scalability, not really vertical scalability. But one thing which has also become important is, as these data sets have grown larger and larger, as more data has become available, the number of use cases where data is applied has also mushroomed a lot. So apart from scalability on just the infrastructure side, a modern day data infrastructure also needs scalability on what types of users and what type of use cases it's able to support. it's not just your traditional SQL data warehousing use cases. It is also machine learning use cases. Streaming analytics is becoming more and more important as well, especially with the emergence of the whole IoT industry, whether it's consumer variables or whether it is in the manufacturing sector. And of course, data preparation as well. So all of these use cases have mushroomed. They have become more complex. They have become more advanced. So as a result, a modern day data infrastructure not only does it need to support horizontal scalability to deal with the volumes of data, it also needs to support multiple interfaces and support for multiple different user personas doing different types of analysis. So if you dissect that further, if you go down, if you dissect that data infrastructure for a modern day company further, you would be able to categorize systems in various different categories as to what is, and those categories essentially follow a life cycle of the data. Data emerges, it's created in apps. It then moves through an infrastructure to collect that data. So that is what is usually called data ingestion. From data ingestion, it then goes into these different systems. Some used for ETL analysis, some used for ad hoc analysis by analysts, some used for machine learning and deep learning by data scientists, and some may be used just for developers for developing certain applications. And finally, the payloads or the summaries arising from these analyses are either used to drive applications or they are used to drive dashboards and visualizations. So consumers for dashboards and visualizations could be your end users who are essentially taking some actions on the basis of those insights. And applications could be anything. Could be consumer facing, could be applications driving certain optimizations, and so on and so forth. So that is typically how different layers of data infrastructure have to be in place for all of these things to be covered to really have a platform which can subsume all these use cases and make big data very simple. What has also happened is because there was a void of systems being able to support all these different types of these different categories at scale with big data, a lot of innovation has happened in open source in trying to fill each of these voids. In almost every in every one of these boxes, there is some open source technology which is available today, and in certain cases, multiple open source technologies are available today, which allow you to solve that particular box's functionality. And when you plug in all these things together, you would get a full-blown data platform or a data infrastructure platform that can solve the big data use cases. On collection side, a standard that has emerged quite rapidly in the last few years is Apache Kafka. There are other technologies also available in the cloud, for example, Kinesis in AWS. But these technologies essentially have really made it simple for collecting data sets, large data sets, generated from multiple endpoints, and putting them in a place where they can then be analyzed. On processing side, streaming analytics has actually undergone multiple different evolutions. Started off with Storm being one of the technologies under the Hadoop umbrella, which was used a lot for streaming analysis. Spark has recently emerged as a technology that is solving this use case, especially because of its strong roots in in-memory processing, which is something that you need for streaming analysis. On batch processing, on classical batch processing area, Hadoop has been there for a long time. Hive attacks that use case quite heavily for doing large-scale data processing in batch-oriented manners. Machine learning, again, Spark has emerged as a strong contender there, and there are a few other projects like Fink which have also emerged and trying to attack that particular use case. There used to be a project called Mahout under the Hadoop ecosystem which attacked that use case. And on ad hoc analysis, you are seeing also emergence of technologies like Presto and Cloudera has Impala and so on and so forth, which are trying to attack those use cases. Net and net, what has happened is in the last I would say 7-8 years, a lot of innovation has happened in the open source stack, where now you have a lot of options available to plug in the holes of these, plug in each of these boxes in a comprehensive data infrastructure which you would be trying to put in place for a company, or so on and so forth. And what we see, at Qubole, essentially, we see a lot of these use cases, and we see, essentially see a microcosm of how different use cases are using different technologies, what are their relative merits and demerits, and so on and so forth. Really, a modern day data team essentially needs all of these things in place. It's not just one piece of technology that cuts across different use cases, but you really need all of these things in place, all of these technologies in place to serve your analysts, to serve your data scientists, to serve your developers, or even to serve your end of line of business users. So that is all great. There's a lot of open source technology available. There are templates that have emerged. There are architectures that have emerged, and so on and so forth. But still, a lot of companies find it extremely difficult to put together this stack, to put together a big data infrastructure. And many times in many companies, you would see a silo of users using big data. It could be a developer team using big data, or it could be a data science team using big data. But it becomes very difficult for a company to really raise the bar and create a central platform which all of these personas can use for accessing data and for doing data processing at scale, both in terms of the scale of the volume, but also in terms of the scale of the use cases. And that is where I think cloud, in my point of view, plays a very, very massive role. Some of the reasons why companies are not able to achieve a true vision of a central data platform that can solve all these problems is because, one, the infrastructure, when you're building this infrastructure on-prem, it is inherently static. There is a fixed capacity that you can deal with. And the result of that is always that the central team which is managing that infrastructure tries to lock it down because the capacity is not elastic. Because the cloud is elastic, it gives on-demand, and it gives you an on-demand infrastructure. It gives you a lot of flexibility for that central team to open up this infrastructure for multiple different use cases. So cloud plays a very, very fundamental role there because of its elasticity, because of its flexibility. It also plays a fundamental role in being a self-service platform. A lot of technologies in the cloud are catered towards building things which are self-service. And really, if a company needs to move to a vision where they want to create a self-service data infrastructure, it plays a very, very central role. Now, putting this stack together, so essentially my message here is that, in order to really, really be successful with big data, I think cloud becomes a very, very strong option to build on top of, to build your data infrastructure on top of, which it becomes a substrate which allows you to open up data to a lot of users and at the same time keep the operational overhead extremely low. However, the way these technologies are built for an on-prem data center versus the cloud are fundamentally very, very different. And I'll just highlight a few differences there to give you a flavor of what it means to make this for the cloud. The very first difference is the storage. A lot has gone into the Hadoop ecosystem to define the de facto storage for big data to be HDFS in case of on-prem clusters. On the cloud, the storage mechanism is completely different. Object stores are the right place and the right technology to store this data because they do a bunch of things. Number one, they make things extremely elastic. So because they are super scalable, you can essentially store data, small data as well as large data, and you can adjust them that way. The second thing is by separating the abstraction between compute and storage, they essentially make compute elastic as well. So you don't need infrastructure to be running all the time. You only need it when you need the processing to happen. So object stores fundamentally are a very fundamental building block of the cloud. And if big data has to be done properly in the cloud, they should be heavily leveraged because they give fundamental advantages in terms of operational efficiencies as well as in terms of elasticity that can be exploited there. Along with the object store, the fundamental building block of the cloud is also elastic compute. I think cloud for the first time gives the ability for infrastructure to fit an application. We have been all taught about setting up an infrastructure and then trying to make the applications fit into the infrastructure. I want to optimize this job, I want to change this because my infrastructure cannot do something like, my machines don't have enough memory or something like that. With elastic compute and with the flexibility that it offers, you can on the fly change the infrastructure to suit the application. And this becomes extremely handy, especially in big data use cases, which can be extremely bursty, which have also a wide spectrum of use cases. So you might need extremely high memory machines for machine learning use cases and very low memory machines for ETL work use cases. So that flexibility also is very important when you're trying to do big data on the cloud, and it's very fundamentally different from what you get on-prem with your fixed boxes that have a certain amount of memory profile or a CPU profile or a disk profile and so on and so forth. So when you combine these things together, an object store and elastic compute, you can get to a platform which makes big data self-service, which is able to do that in a completely on-demand manner, which also future-proofs any evolution that happens in any of those projects or any evolution in your use cases because of the fundamental flexibility of the cloud. Now, one thing that is constantly brought up as a counterpoint is, hey, how secure is my data in the cloud? That picture is also very, very rapidly changing. AWS has a lot of product features built around encryption. So have the other clouds. There are a lot of product features built around compliance. And fundamentally, when I talk about this, these are just some of the features that have been implemented on the cloud to address security. But fundamentally, when I talk about this, I always give people an example of whether they think their data is safe in their own data center versus a cloud data center. And the analogy to draw here is: do you store your money in a safe in your home, or you put it in a safe in the bank? Some of the best practices around security are undertaken by the cloud providers. And as a result, I feel that this thing, the security perception of the cloud is changing very, very rapidly. So it becomes an even stronger option to build and put together a unified data platform, which has all these different engines plugged in for various different use cases, all provided within a secure environment. And I think that is where most modern data teams should aspire to and should run towards in order to make big data successful for the enterprise. So I'll pause there. I will stop there and pass it over to Rob, who will talk about Flipboard and how they're using big data at a much lower detailed level. This is a much more high-level picture, but he'll talk about a lot more details around usage and real-world use cases.
Great, thank you. Can everyone hear me? Okay. Definitely some really good points. You see now that people, we're not using transactional data anymore, we're using interaction data. So if you remember, like, no one was using, people weren't using phones a while back. And now everyone has a device. So we have insane amounts of data going through our platforms, and we need big data tools to analyze those large data sets. Let's see. Okay. Sorry. Okay. So I'm going to talk about how we use big data at Flipboard. And first, I'm going to give an introduction to Flipboard and tell you what Flipboard's about and what our aim is as far as how we envision the user experience, and then I'll talk about some of the techniques and some of the products we use as far as a little bit of information about how we use Qubole and a few other tools we have available to us. So talk a little bit about Flipboard. So Flipboard is a news aggregation or a news recommendation platform. So we think of Flipboard as a place for your interests. What this is the first launch experience in Flipboard. So how it works is you open up Flipboard for the first time, and you're prompted to this kind of like this questionnaire and asks you what topics you're interested in. And this person chooses news, crafting, entrepreneurship. And what we aim to do is take some information using your usage data and the information we get from this questionnaire and pipe really high quality articles to the reader and make it to where they have a really great experience in reading nice long form content. And there's another component of Flipboard, and that is we work in the area of collection. So you can collect things on Flipboard, and you could add news articles to what we call magazines. So you can create your own magazine, and your friends can subscribe to it, and they could read the things you're reading. And you could have your own point of view exactly as far as what your take is on coffee or surfing or mountain biking, and other users can consume that. And it's kind of like a social ecosystem around content. Basically what we're trying to do is whenever a user uses the application on their phone or on the web, we're taking into account their interactions with particular entities within Flipboard. So we'll look at a user, and let's say this user reads 10 articles. What we try to do is we try to take the usage data that they provided to us and then come up with a good strategy to where next time they enter the application, they're presented with even better material. So basically the idea is that Flipboard learns your preferences as you use it more and more. All right, so right now we have about 80 million active readers. So that's 80 plus 80 million MIR. And so as far as the data infrastructure, or it's part of what my job is, I'm a data scientist at Flipboard. So I work a lot in recommendations of these particular entities like magazines, articles, topics. So there's two different sides of the data pipeline. So one side is the ETL process and working with Hive and getting all the data into our SQL data store, which is Amazon Redshift. And that serves as our analytics platform, and that feeds into a lot of our tools for analyzing A/B tests, looking at our particular, let's say, our MAR number over the course of the last year, and just basically serving as an analytics platform. And there's a few other recommendations to products coming out of the Amazon Redshift data store, but most of it actually comes from our recommender index, which is pulled from, the data is pulled from S3 and then moved into what we have, a graph database. And this graph database produces recommendations. So that's whole nother topology or pipeline. So, okay, we have ETL reporting. All right. And here are some of the tools. Is everyone mostly a Python person here? Or any Java people? A few? Okay. Yeah, so we use Spark. Spark streaming, actually, we're not using this for production ready tools or anything, but this is something we're starting to implement. And Spark is actually kind of new to Flipboard. We haven't been using it that long, but we have been using Hadoop and Hive for a long time. And SciPy and NumPy, these are a lot of things I work with as a data scientist. They're generally in memory, and we do a lot of our prototyping on our in-memory, do a lot of in-memory prototyping, you could say. Okay, so I was going to talk about, people ask the question like, why use Python for data? So Python has a lot of really great libraries. There's a really great community around Python, and it really lends itself well to data analysis because the scientific community uses Python a lot. And what's nice is that Python is a language I feel that an analyst or someone that may be an expert at using Excel or SQL would be able to pick up Python fairly easily, and I could show in this example. So I'm just going to talk about the word count example, which is just a MapReduce job for counting the words in a corpus documents. So you can see here we just have two programs. So we have a mapper and a reducer, and then the mapper is reading line by line in a file, and it's splitting, and then it's adding one. It's creating these tuples of a word and a one, and then the reducer is combining these together and grouping them. And what's nice about this is that you don't actually have to know anything about inheritance, or you really don't even have to be that. You don't have to be a programmer, let's say, with a degree in computer science or something. You could pick up Python, and it's something where you know the inputs and outputs, and you know what you want as a result, and then the rest kind of comes a little bit easier than using a compiled language. So yeah, you understand the standard in, standard outs. You understand looping, going line by line, and you just need to know how to run this and where to run it from. So this is word count in Java. I'm sorry, this is kind of small, but you can see there's a lot of you have to understand classes, the concept of inheritance, and a lot of these other entities within this language that may not be as easy to understand to an analyst as opposed to a programmer or someone who's went to school and learned C++ or Java. And I think now most universities require Java as a language, compiled language. So this is actually kind of something kind of new. I'm not sure why they chose this, but it's kind of like an industry standard, having everyone learn Java. So word count in Java, you need to know about objects, classes, inheritance. There's a context variable. There's a lot of boilerplate code in this example. There's a lot of things to import. So it just makes it that much larger of a barrier for analysts or people that are new. And also there could be other people, math people that don't have programming backgrounds that need to learn all this. So we just want them to hit the ground running and be able to start doing data analysis with Python. So there are a few advantages to Java, obviously. It's faster. It is more modular. I know that YouTube was using Python for a while, and now they're kind of moving on to Go and using Java because it's packaged a lot easier and easier to send around. And like I said, more programmers know Java than many other languages because of the kind of the requirements. When you're in school now, you have to learn Java. Okay, so this is the part where I'm going to talk about our data stores, our pipelines running from S3, and where the sources and destinations are and how they get from point A to point B and all the transformations we make with our data. So usage by far is the most important component of Flipboard's data, because without usage we don't really have a product. And if an hour or two goes by and we don't get usage data, that's like a serious problem. That's like everything has to stop. Like that has to run every hour. And this is something that all their usage pipes into our products. So we basically can't have products without our usage data. So we have two different pipelines. One of them is the Redshift pipeline. So that's the one I talked about earlier, which is our analytics platform. And a lot of this data lives in S3, and it's in a JSON serialized format. And we do some transformations on it, and then we turn it into, put it into a kind of like a column format, and then insert that into Redshift. And then there's a lot of products we have that pull from Redshift. The other one is the recommender index. So that is a kind of like a separate data store, a completely separate pipeline. And it still reads from the same location. It reads from S3, and we have a collector which collects all the data and transforms it, and then throws it into Kafka. And then the recommender index, or the graph database we use, our graph database is what houses all of our recommendations and our latent factor models and basically all the tools we have for providing recommendations to users. So that server reads off of Kafka and then updates in real time. So if we have some new interactions from a user, it might be an hour or two, and then we're able to provide recommendations based on that new knowledge. Okay, so a little bit about a recommender index. It's in memory. This is the graph database, and it's just one giant box. It's about, I think, 250 gigs, and we run all of our optimizations in memory because it's very fast. And a lot of what we do on a recommender index has to do with clustering. And we have a few collaborative filtering models running on there. And we also have every user's latent factors or every user's information on their usage condensed into these factor models, which provide us with a good means of providing recommendations to users. And so we're talking about Redshift. So this is our ETL setup for getting data into Redshift. So we use Qubole, and there's just two steps here. You have a Qubole configure, and you can create a Hive command running this hive command.create. Ashish is a better person if you have any questions on that. And so this is this Python ETL setup. This is basically what executes whenever we want to run a job on Hive. And you see here it's just we have a few attempts that run, we have a timer, and we have a hive command.run, and it runs this query that's passed in to this execute. Yeah, I'm sorry, this is really small. So this is just a general, so this is part of the Redshift pipeline. So this is just a general execution of this query. So whatever query you have, and if you want to run it on Hive, this is what runs it. So I'll talk about the process from our data usage, our usage data straight into Amazon Redshift. So this is our usage data pipeline. It comes in through S3, and these are just rows of JSON data. And then it's deserialized, running through a Hive job. There are some other operations that happen on the data, like there's some IP to geolocation, user-defined functions that get added. And once the transformations happen, it gets put into kind of like a columnary format and stuffed back into S3. And then from S3, there's a process that takes it from S3 and then puts it straight into Redshift. And then from Redshift, that's where a lot of our analytics platforms consume the Redshift data store, as well as like ad hoc queries and things. Okay, this is just the process that puts it from S3 to Redshift. I'm going to talk about, instance management here. Okay. So we had previously we had a bunch of Amazon reserved instances on this VPC, and we manage them ourselves. We actually don't. We have about, I say, 3 people on the data infrastructure team now, and having a fixed size VPC, you have to manage everything yourself, and there's changing requirements all the time, and it just gets to be unmanageable and unwieldy. So it's something that it really helps us to have some type of auto-scaling, and the infrastructure that we use with the cloud is something that's really nice for us because we spend a lot less money on reserved instances, and if we're not using an instance, we don't have to pay for it if we're not running a job on it, which is really nice. A lot of these jobs, we run them on Qubole, and as far as configuration, tearing down or bringing up instances, Qubole does that on the fly, so we don't have to manage that as well. So that's also really nice. And talks a little about auto-scaling. We have a dynamic data infrastructure, And so we have all the jobs running on the same cluster. If there's, let's say, 2 jobs running at one time, if there's a new job that comes in, the auto-scaling deals with the demand of this new job and then kind of comes up with its own strategy to handle running these jobs all at the same time. So with running on Qubole, Qubole is, the instances are hosted by Qubole but owned by us. So whenever we're running a new job and we need more machines, Qubole provisions these machines on our behalf and then decommissions them as the job is finished. And that saved us a lot of money in the past, and this is something that we're really happy to have. Okay. So this is one application we use with Spark. So we have a follower suggestion recommendation within Flipboard. So as you're going down your top stories or your main feed of articles, we use a recommendation module that pops up, and it's basically a user recommendation module, or like people you know on Flipboard. So this uses Spark Graph. So what we were doing in the past is we were computing follower suggestions using Hadoop, and this took somewhere around like 40 hours or so to complete, and sometimes it wouldn't even complete. And this is a lot of the reason why this happens is because MapReduce is not in memory, so it takes a really long time to get through a clustering algorithm. So we moved everything to Spark, and what's nice about Spark is that everything's in memory. So these connections from user A to user B, or they're basically seen as, instead of being on different partitions, each user is seen as being, each connection is seen as being completely separate. So each, let's say you have a node of a user. This node is, if it's referenced many, many times, it's able to sit in memory, so that way you can access it easily. Okay, so this is, so we use Spark, so this is talking about the how long it took for the Hadoop job to run. So 40 plus hours, the Spark time was 20, 30 minutes. And it treats vertices individually and uses caching and holds on to the most visited. So as you imagine that if there's a user that's very popular on a particular social media platform, that user's going to be accessed more than any other user. And it's better to have these nodes decoupled, so that way they're not just living on one particular partition that you have to revisit over and over again on disk. So this makes computation time a lot faster. No, I'm talking about a user. So like a social media connection. So there are nodes and edges, and let's say if I'm following you on social media, then I would be a node, and there'd be a directed edge from me to you. Okay. I'll talk a little bit about Spark streaming, and then I'll do a quick demo at the end. And the demo is of basically just a topic cloud of user affinities. So a user has particular affinities to topics, and then basically the more affinity a user has to a topic, the larger the node will be. And I'll show that at the end. So this is basically an interest graph visualization. So our interest graph pretty much feeds into a lot of our products, and so each user has a topical affinity vector, and we use this topical affinity vector to feed you articles, topic recommendations, and magazine recommendations, as well as it serves our ad platform as well. Okay, so this is a real-time demo. It uses Spark streaming. So it listens to Kafka and reads events that read events for like articles. So if a user reads an article, we look at what topic the article is in, and then we change the basically the size of the affinity for that user to that topic. And so there's just a few steps here. This is it creates a streaming context and reads from an input data stream from Kafka. And based on the user's time within an article, it applies more weight to that article. Let's say if the user is reading an article for 10 seconds, there's a larger weight than if the user goes into the article then jumps out of it. So the reason why we chose this is because users that click into an article then jump right out, that may be a sign of clickbait or some type of content the user is not really satisfied with. So when the user jumps into an article and reads it for a while, we assume that the user has a higher affinity to that topic, and we apply a larger weight. And let's see. And I'll show you guys this tool. Let me connect to the VPN first. So let's see. I can get this to show up here. There it is. So make it smaller. So these are the topics of Flipboard. For this particular user, you can see that they read more articles about Google, machine learning, psychology, and from these sources, Huffington Post, Business Insider. So this is reading from Kafka, and it's giving, for each user interaction with an article, there is a certain weight applied to a particular article or a particular topic based on the article's topic. So a few other users here have different topical affinities. These users' topical affinities are more general. Yes? Oh no, this is something that was developed internally. So I think it's just reading off of Redis, and so this basically just shows you what the person's interested in. This is like an interest graph for one particular user, and you can see here they follow read a lot of space, photography, Apple News, and Facebook articles, and it just gives us a good idea exactly like what users are interested in and what this user might be inclined to buy. Like if we wanted to show them an ad, maybe they're into photography, we'd like to show them an ad for a camera. And the more we know about users' topical affinity and their interests, the better job we can do in providing with articles and content they're interested in. And that concludes my my talk. Do you guys have any questions?
You mentioned that you took the user data and put it into S3, but it's file storage. So how do you get from your application data to S3?
So we have so from the devices send to one of our servers, and from there we have what we call a flap server, which this is the server, the infrastructure that talks directly with the phones and all of our devices. So from there, the data is being sent to that service, and the service is taking it, putting it into JSON format, and throwing it into S3, and then from there we consume it.
So like when you consume it, so that you would combine that usage data with like the existing data and then put it together in storage as one file, or?
So it's in, basically you could say it's not really in real time, but it's in it's basically chronologically ordered. So whatever we have in the, let's say, a recommender index is all of the data and all the usage for a particular group of users up to, like let's say an hour ago. So whenever we get new data, it's put into to Kafka, and then whatever the last hour of usage is, it gets put into our recommender index. So that way we could, I mean, users don't generally come every hour or so, but we'd like them to. But it's something to where you have data up to a certain point, and then we just keep on feeding more into it, feeding the most recent. And generally, as a rule of thumb, we don't try to analyze, like, let's say if you're a user of Flipboard for the last 4 years or something, and we don't actually just try to analyze the last 4 years of your interests and every article you've ever read. We just look at the last, let's say, like a few months or something, or 6 months of interaction. One, because your interests change over time, and two, because we have to we analyze less data, so we use a sliding window. Yes?
You're doing the map reduce still on the with Hive, so in a Hadoop box, or in this case, you're saying also it's a Spark. Why is that? Are you trying to move to Kafka, or is there some stuff that Kafka does that I'm not sure of, or in addition to?
We just use it as a let's see. We just use it as a queue. So basically, we just want to read the most recent usage data off of this queue, and we want to update our recommender index in all of our stores using that. So yeah, just the most recent usage data is living on there. And also, we also use SQS. We're trying to move over to Kafka, but our SQS queue, we're throwing article content on this queue, and it's also being consumed by the recommender index. So recommender index also has our topics. So for each article, we're able to get a ranking of topics for that article, so that way we can have a better idea exactly like what the article is about, and so we can also send it to the right people who are interested in reading it. So, yeah. Yes?
You just mentioned that you were moving from SQS to Kafka. Maybe you could go into more details as to why you're moving from SQS to Kafka?
Well, SQS is really expensive.
Is that the major reason? That's just price?
Mostly, yeah.
And it's not because of like any better compatibility between Kafka and Spark?
I'm not sure. For what I understand, the reason why we're doing it is because we already have Kafka, and if we're going through the trouble of maintaining it and using it, then we might as well just use it for one extra purpose instead of having to pay Amazon more money. So we probably spend about $1 million a month on AWS. So it's a lot of money. We don't want to have to pay more for something we could already we already have the means to deal with right now with using Kafka.
And I guess you get consolidation of infrastructure, right? You don't have to have separate skill sets to manage different parts, right?
Yeah, I mean, we really don't have that many people on the data infrastructure side, so it really helps to have like a few chosen tools or our favorite tools that we want to use.
I think also at a larger scale, when your scale increases, is the same reason why people move from, say, MPP databases towards Hadoop and Hive. As your scale increases, SQS technologies become less scalable as compared to what Kafka and those things will offer.
Basically what I was trying to get at. Is that the reason why?
I don't know about their reason, but what I have seen is generally, as the scale increases, you need to start moving towards these technologies, which are more catering towards, higher volume data and stuff like that. Now, of course, there's stronger integration with open source projects also. That also helps. So I think it's a combination of both. But primarily, the places where I have seen moving from these are all message. You could think of them as message buses, right? So moving from an enterprise message bus to a cloud scale message bus or a web scale message bus, which is where Kafkas of the world reside, usually happens because of volume.
Yeah, good point. More questions?
Sorry, once you have all this, you have like the relationships and their recommended their topical affinities. So how would you get that data and then use it in your application to process it and then have the generate recommendations and then store it Redis and then is that user or
Yeah, that's a really, really good question. So there's a lot of parts there. So, oh, I'm sorry, let me repeat the question. So she wants to know how we use Topical Affinity to recommend content to users. And she also is asking, there must be more to that besides just looking at the topical content and then giving recommendations, right? Kind of. So there's basically two components. So if you look at on a high level, for recommender systems, there's usually two types of approaches. There is, let's just say in news. So there is the topical component, so this is content filtering, and then there's collaborative filtering. So content filtering has to do with the content of the sample. Let's say that I want to recommend a news article to someone, and the news article is about big data and machine learning and Elon Musk. So what we do is we could take the article and extract topics from it and create what's called a topic vector for that document. And we could use that information in the future whenever we want to generate recommendations. So you can imagine that you have a topic vector of size 40,000 and a user's topic vector, which represents their topical affinity for all different types of topics, is the same size. And you can just perform a dot product on those two vectors and you can come up with a score. So you can imagine that you have, for a particular user, you have this vector, and you basically match this vector against the last 50,000 documents or 100,000 documents that came through the pipe recently, and then you could just sort based on score. So that's just the content part. The collaborative filtering part is a little bit more advanced and a little bit more powerful in that it looks at the users that are similar to you based on your usage history and creates kind of amoebas or like clusters of users around the content or around the usage. So in order to facilitate this, we use an alternate least squares algorithm, which is an optimization algorithm, and it's also known as a latent factor model. So what a latent factor model is a model which could take a bunch of user data, which is, let's say, a large, I don't want to say matrix, but you have, let's say, a lot of users and then a lot of documents. And for each one of those users, they have a particular score for each one of those documents. So what you can do is create, after you're running this optimization, you can create a bunch of factors for each user and then factors for the documents. And what these factors represent are the interactions with the user to the content. So, and you basically, same way as collaborative filtering as we do with content filtering. You match these factor vectors that represent the user in the document, and you go through each one of these documents and you come up with a score and then you rank them. And we merge both of these models together to come up with our recommender system. And you know, the usage, the pipelining and everything kind of lives on this graph database that I talked about earlier, and that's where all the optimizations happen and where all the factor models are computed. Does that answer your question? Oh, so the algorithm, I can't tell you exactly which one it is, but it's an alternate least squares algorithm.
Alternate least squares?
Mm-hmm.
Okay. Thank you.
You're welcome. Yes?
What infrastructure are you using for the graph database?
So our graph database is internally developed. We call it Podex, and it was written in C++ by one of our developers, and we have Boost libraries written in Python. So basically, you could act on this database like kind of like natively in Python. It almost feels like, but under the hood, it's all running C++. It's really fast. It's just one giant behemoth box, and all the data lives in this box, and it's just a large amount of memory on this instance, and that's pretty much all we need for doing this.
I guess the person that designed it, you want to roll out a solution for using something like what's usually used for this, like Neo4j. Is that right?
Yeah. Well, this was actually before Neo4j, is before a lot of things. I think I'm not sure what year it was written in, but it was before all of these different tools. So, like I guess I could explain like how it would be used. I go into I create like a database instance or a database object, and create a so I have this DB object, and I could just type db.user and then brackets and just like a dictionary, grab like a user ID or pass in a string, like just string user ID, and it comes up with, all right, I have this user, which is a node in the graph, and then I could say, okay, I'd like to go through all the views for this user, all the topics, or all of the likes for this user, and basically any, their magazines and anything lives within this user's, this part of the graph, and it's really useful for analysis, and it's a lot more useful for doing certain things, like getting the most recent chronologically ordered documents or likes the user had, and it's a lot better suited for recommendations than, let's say, SQL, because SQL is just one giant, spreadsheet almost. So, but yeah, that was a good question, and I don't think he's gonna. I'm hoping he's gonna open source it soon. I've been pestering about it, but if it's maybe it's something he developed that he just wants to bring whenever he goes to a new job or something, or maybe he just doesn't want to have to support it, because there's a lot of work with supporting something like this. I think it's probably like 4,000 or 5,000. No, it's not, and it's just in memory, so it's not like, yeah, I haven't dug through it yet, but
If it works, it works. Right?
yeah, it works really well. Works well for our purposes.
Do you do MapReduce in Python? You had that example at the beginning, but are you doing MapReduce with Python?
Generally, that's written in Java. And for ETL, it's mostly Java. Well, no. For ETL, that's in Python. I can't remember exactly. Yeah, it really depends, I guess. But like for whatever I showed you there, the ETL going from S3, that's all in Python. So.
But are you doing any kind of distributed processing on your Python code?
Like what types of distributed processing? Well, we're doing Hive processing. There are a lot of jobs running. I'd probably be a better question for one of our data infrastructure people.
Seems like a good marriage between you guys, two different companies, right?
Yes,
Is Qubole.
Mm-hmm.
that's right.
You guys are doing this ad platform, let's say, to the magazines, the recommendations. How did you guys happen to, run into each other to do this business? Because one fits very well with another. You guys part of the same team before?
No, I think we are more of a provider,
Mm-hmm.
and they use our platform to do that. How did we discover ourselves? I don't know.
And I just met you like an hour ago, I think.
Yeah. But I guess there is a pain point and there is a solution to that pain point, and essentially that's how we came together. So we specialize a lot more on big data on the cloud. Flipboard is using the cloud very heavily, and that's where the intersection happened.
Mm-hmm.
Like some things that you talk about in Qubole, it sounds like with Juju and Charms, you're orchestrating, spinning up boxes to do your job and stuff like that. But this is more at a programmatic level from what I saw in Juju.
So there is a programmatic interface to Qubole, and then there's the infrastructure orchestration piece behind the scenes. So the thing which cloud allows you to do is to create infrastructure on the fly. So if you marry the programmatic interface with the orchestration piece, you get a very powerful paradigm where everything is created on demand. It fits to the purpose of your application.
So is this something Juju doesn't have?
What doesn't have?
Juju doesn't have this ability. It sounds like you can spin things up, spin things down, and not needed.
Yeah, so this is autoscaling. So it's not just spinning things up and spinning things down. It's actually spinning things up and down based on the demand. And so there are algorithms there which figure out, okay, we probably need more machines, or we want to shrink it down. And then autoscaling in a stateless application is easy. In a stateful application where data is involved. So if you are scaling down Hadoop clusters, for example, you knock off a couple of replicas, and then what happens to that data? So you have to make sure that there's complexity involved around data placement and stuff like that. So that is a central part of our orchestration piece. And when you're using the cloud, so companies like Flipboard and all can write applications on top of this, which are doing these higher value things, where you're creating these affinity graphs and recommendations and stuff like that. So behind that application, there's a whole pipeline of things, and one part of that is solved by Qubole, and another part is solved by the graph database and stuff like that.
Sort of follow-up question: are you using some kind of configuration management software behind the scenes, or are you just programming straight into AWS?
We are programming straight into AWS because a lot of configuration management software is general purpose, and when you're doing something very specific to big data, then you need access to the daemons and the data, or the states of the daemons to know. Those are the inputs that go into the prediction algorithm to figure out how autoscaling has to be done. So we use we've kind of built that out.
Cafe?
Cafe. So is this agnostic, so I can use Cafe library to network?
So yeah, you can use a Cafe library to use in our networks, but in what context? You mean like in the cloud?
For the Qubole, it looks like what they have is specific Hive support, use support. They're using Python. If that's not supported by Qubole, does that mean I'm restricted? I can't use other machine learning type of packages like R, so on and so forth?
I mean, I don't know. I mean, it's I think that I built a Cafe box with CUDA, and I had to build everything myself. Are you guys looking to go more in that area, or?
So we do support integration with R, but we have not looked at Cafe as such. Now, the platform allows you, you have to draw a box as to what is supportable by the platform and what is not. We essentially draw a box around around Hadoop, Spark, Hive, and Presto. Those are the 4 technologies. Now, you can use Cafe libraries through or any generic library. You can absolutely use that in Qubole. However, that has to fit into the paradigm of one of these infrastructures. For example, do you want to write a Python streaming job in Hadoop or Spark using Cafe or any of these other libraries? You can certainly do that, but that becomes beyond the scope of the platform itself. So any programmatic library that you want to use, like MLlib, a lot of people use MLlib with Spark. You can use that with Spark,
right,
and stuff like that. So that's programmatic interface. That programmatic interface talks to our interface, which is around job submission, execution, results, movement of data, and so on and so forth. That is the interface that we provide. Below that is the orchestration piece that happens.
Yeah, so I guess it depends on what level you enter.
Yeah.
Right. That's very very focused. So I'm sure you could use Cafe for many other things, but what I use it for is for a deep learning network, and that just basically, it looks at an image and classifies it into one of 1,000 different categories. That is so niche right now that it's not even useful. I mean, for us, it may be useful for a few other companies, like a camera company or like Dropcam or something like that. But I think maybe soon the adoption will be more and more with deep learning, and but I mean, it's still at the level you guys are at now, you could do it. But I think, does MLlib have any? I think MLlib has some deep learning stuff now, but I'm not sure.
Expert on that, but I'm sure there is something.
I don't know if anyone uses that. But Cafe? Oh yeah, I mean, you could set up with a GPU, but you have to do all the management yourself.
Yeah.
If you're doing it straight up like that, and it's like I set it up. It took me about a day. It's a lot. And actually, they killed my box because I wasn't using it, so now I have to set it up again. That's what happens when you don't, you know. What's that? Oh, I haven't used Docker yet. I've had the pleasure. I think you can. I use an AMI, so Amazon Reserved Instance, to set it all up. It makes it a little bit easier, but yeah.
I think we are out of time. Is it?
Yeah.
Okay. Thank you
Thank
very
you.
much.